ds. And we also found that S is a state function. It's called entropy. Okay, it's a function of a volume and temperature. For a reversible process, ds is dq over t, right? And for an isolated system, this is going through this very fast because we did this last Friday. For an isolated system, there is no heat transfer into the system, right? Because you can think of the whole universe or the system of interest, where in the time scale of interest there is no heat transfer. Then ds, because this is 0, ds has to be greater than 0, right? So we can analyze this into three parts. When ds is equal to 0, it's a reversible process. Okay. When ds is greater than 0, or delta s is greater than 0, then the reaction happens spontaneously. You know, it will always happen. It will reach a state of maximum entropy. That's the statement of second law. And then if you calculate ds to be negative, then it won't happen because it violates the second law. Okay. Any questions so far? This is the main thing, right? And the beauty of it is that, I mean, we won't have time to, in fact, we won't actually pursue it. I mean, entropy is kind of a naturalist concept, you know, it takes time to get used to. By knowing entropy, you can actually build, construct a lot of thermodynamic potential. Concept like Gibbs free energy, Hensel free energy that you discuss in chemistry. And when you do that, after you do that, then you don't have to worry anymore whether your process is reversible or irreversible, right? All you need to do is, in this case here, calculate entropy, and if you want to stop at entropy, then you just realize that if ds is 0, then it's reversible. If ds is greater than 0, it will always happen. If ds is less than 0, the whole thing doesn't happen. Okay? For this engine or any process, chemical process, whatnot, right? In particular, we discussed this briefly at the end of lecture last week for an isothermal expansion or even a Joule-free expansion, right? This process, the isothermal process is reversible. The Joule-free expansion is irreversible, right? But to calculate entropy, you don't really care, right? Let me show the diagram here for isothermal expansion. The initial, the final, right? All you need to do is to be able to connect the initial and the final point with the reversible process, right? Because entropy is a state function. If you know how to connect the initial and the final with the reversible process, then you can always calculate the entropy change, right? So in this case here, because it's an isothermal expansion, then it's already reversible. You just go through along that path, and you find that the entropy of the change in entropy of the system alone. I'm not counting the environment yet, right? So it's not the whole universe. It's just the piston is given by nk log of V final over V initial. Okay. And same for the Joule free expansion, right? I don't know how the irreversible path goes from initial to final, right? But I can always calculate the entropy change, right? As long as I know how to connect the 2 points with a reversible path. And for this, I'll just use the result from the isothermal expansion, right? Because it's a reversible path, then it has the same entropy change, because it has the same final state and the same initial state. Okay? And just in particular, if the V final is twice V initial, then the change in entropy is n log 2.
I'm a little confused because if entropy is the state function, it only depends on its initial and final position, then how is it that you can have the integral from A to B or dg over t, how can you have the entropy be greater than that? Because wouldn't it just have to be different between B and A?
Yes, the entropy change for a process, right? You go from here, right? It's just the entropy at B minus the entropy at A, right?
Yeah.
But you have to calculate it, right? To calculate this, you have to find a reversible path from A to B.
Oh, okay.
Right.
So it's just not necessarily equal to the integral of dq over t.
It is. It is an integral of dq reversible over t
Oh.
over a reversible path. Right? I have to find a reversible path. If I cannot find a reversible path to connect from A to B, then I don't know how to calculate the entropy change.
Right.
Right?
Okay.
At least classically, or classical thermodynamics, but you can always use it from statistical mechanics and calculate the entropy change there. Is that what you're referring to? If you pursue this, definition of entropy from the consideration of kinetic theory or statistical mechanics, right? Then you can calculate this.
Well, I guess
Irrespective of the macroscopic thermodynamic process, right? Because this is just counting from the perspective of statistical mechanics. The entropy is just counting, right? So if you can count the state at B and count the state at A, then you can find the difference. Yes. But we're not doing it that way. This equation has to be true, though. If it's reversible, if it's not reversible, then it becomes like that.
But okay, what I don't understand is like even if it is irreversible, wouldn't the integral from A to B of dq over t still have to equal the same entropy change because it's the same initial final state? So I don't see how it's
Yes. If it's irreversible, then this is this is here.
Yeah.
This is true, right? For the inequality comes if dq is irreversible. If this integral is irreversible, then this is true. Right? This we prove from the consideration of the Carnot cycle, if you remember it. Does that answer your question?
Yeah.
Okay. Any other question? Michi?
So I thought you said the dual free expansion was an irreversible possible. So how would you find a reversible path?
I just need to find a reversible path. So there is these 2 points, right? V initial and V final. Okay. This is pressure. Okay. I don't know what the irreversible path that takes you from point A to point B.
But if the process is irreversible.
Right, it's irreversible, right? So at any point, there is no well-defined macroscopic thermodynamic variable, right? Except that only at the beginning and the end, I know. Right? So if I know these 2 points, I don't know the irreversible path, but I can always connect it reversibly, right? Or some other path, doesn't matter. Right? But I happen to choose the isothermal path. Right? For a reversible process, because this is always true, right? We discussed a lot about this, say, in electrostatics, right? Because this is always true for a reversible path, right? It doesn't matter if I go through any path, as long as it's reversible, it will give you the same answer. I choose the one, I choose this one. I choose the isothermal expansion to connect these 2 points. Okay? And I know how to calculate that. Okay? And the answer is the same. Because the answer only depends on the initial state and the final state. That's the beauty of it.
How do you look at a path on the graph and just know that it's not reversible?
This is just a caricature, right? Meaning that from going from here to here, right? In the intermediate states, it's not well defined. There's no well-defined thermodynamic variable that characterize the system.
So it doesn't depend so much on the graph as much as the information you given in the problem?
Yes. Yeah. I mean, the problem with that is a reversible process, or I mean, by now you should know, say, Joule free expansion is irreversible. Also, the next example, hopefully we can finish this in 5 minutes. Suppose I have, remember this discussion, right? If I have T1, T2, two metal, right? T1 and T2, okay? And if the T1 is different from T2, it's delta, okay? So there's a heat transfer going down, right? If the thermal contact. Right? And this process is irreversible. Right? You can never go down unless T1 is equal to T2. Right? Okay? So that's what we want to calculate now for the next few minutes. Suppose I have a reservoir, say of water or whatever, right? A reservoir. Right? So whenever I say a reservoir or heat bath, then you know it's basically for the purpose of the problem, it's an infinite body, right? The temperature doesn't change much, right? Reservoir is like that, right? I drop a piece of metal. So that's a piece of metal of temperature T, call it Ts, right? That will be inside Ts. And so Ts is greater than T dot, right? Okay. What's the entropy change? When we calculate what's delta S. Also, what's delta S for the reservoir? Okay. So how do we do this, right? First of all, there's a finite temperature difference here. The whole thing is irreversible, right? You cannot calculate it, right? So how do you do this? The way you do this is, at the end of the day, right? Initially Ts is equal to Tr. But once everything reaches equilibrium, what happens? Initially, and when things reach equilibrium, then they have the same temperature, right? At the end of the day, S is equal to Tr, right? Okay? So there is a heat transfer, right? There is a heat transfer from the, in this case here, from the system into the reservoir, right? Okay? So how do you calculate that? To do that, all you need to do is start with you do it reversible, right? You do it reversible, right? You know at the beginning it's at Ts, right? At the end of the day it's at Tr. Right? So what you do is so this is your system. Put them in a thermal contact with a heat bath. Ts minus epsilon, right? And then once they thermalize, then you put this Ts with this metal, Ts minus epsilon, is Ts minus 2 epsilon, and so on, right? This is the graph, right? Ts minus 2 epsilon, thermal contact with the Ts minus 3 epsilon, all the way until you reach Tr. Right? Okay, so you do it slowly. Right? And at the end of the day, you don't care about all the back. Right? You only care about the system of interest. Okay. So when you do that, we know that for the metal at least, then dq is just the heat capacity C, right? So usually it's the unit mass, right? So this is just usually mass, then times the specific heat, right? called this? Molar? Not molar.
Heat capacity? Molar specific heat?
Not molar. I don't want to use molar.
The regular specific heat? Okay. That's all there is.
Mass and heat capacity per unit mass, what's it called? It's specific heat, yeah. It's a specific heat. Yeah. Okay, yes. Right, okay. So, anyway, let's just use heat capacity. And dq is just C dt, right? Okay. And delta S then is an integral from initial to final, right, of dq over t, right? Then this becomes C initial to final dt over t, which is equal to C log of t final over t initial. Right? And in this case here, T initial is Ts, right? And T final is Tr, and Tr is supposed to, it doesn't really matter, right? But it's supposed to insert a hot metal into water, right? And Ts, Tr is less than Ts. So this becomes C log of, what is the final? Tr over Ts, but since Tr is less than Ts, this is less than 1, this is less than 0, less than 0. Okay, it is clear? That's the entropy change. Let me erase this, so you know what's happening here. Delta S of the metal, that means explicitly write the minus sign, right? By inverting the log. C log of T S over T bar. Okay. That's the entropy change of the metal. It's a negative entropy change. So, but then we know that if entropy change is negative, it's valid the second one. So what's happening here?
The heat path is gaining entropy that's larger than the normal species.
Yes, and then there is the reservoir itself also has an entropy change. Right? How do we calculate that? And then the sum, delta S of the universe, is zero in this case. And we can prove that. Right? How do we calculate the entropy change of the reservoir? Let's take some time to calculate that. The reservoir is always at a constant temperature, right? It's always at Tr. And then the heat in this case here, suppose Ts is greater than Tr, the heat is going that way into the reservoir, and the reservoir never changes its energy, right? So the entropy change of the reservoir is just going from initial point to the final point of dq over T, right? But the T here is just the T of the reservoir. It's just Tr. It's 1 over Tr, initial to final, times dq. Okay. So what is this integral here? This integral of the differential heat transfer from initial to final is just the total heat transfer from the metal into the reservoir, right? What is the total heat transfer? Total dq or total q is just the specific heat times T, Tr, or Ts minus Tr, right? We can do this, but I just assume that you guys all know this from high school or from chemistry, right? This is in chapter 17 or 18, right? Total heat transfer is proportional to the specific heat or heat capacity times the temperature difference, right? And in this case here, the heat transfer is positive into the reservoir, right? You add heat into the reservoir, so this is positive. Ts is greater than PR, so this is positive. This becomes a C, Ts over PR. And this whole thing, delta S of reservoir, becomes C. Am I missing something? No, right? This is a specific heat, C times Ts minus PR over PR. Okay? And if you add these two equations, you'll always get a positive number. Because I can just graph this in a calculator or in a computer. Is this clear? Do you guys want me to do this? The sum? No? You guys seem confused? But yeah, I mean, if you just grab it or you just use some small temperature change approximation, you can always show that the sum is always greater than 0. Yes.
Shouldn't Q be equal to NC Ts minus Tr, or just assuming N is 1?
Wait, say it again?
Q.
Oh yeah, sorry, I'm not very good at this. I guess I'm always using big C, right? But you have to be careful, right? No, it does matter, right?
Okay.
Right, but this is the heat capacity. I'm using this big C. But big C is just a small, this is the mass times the specific heat. Right? Sorry for this, but yeah, this is apparently throughout my lecture, I'm always using extensive variable for specific heat. Yes?
So when we are calculating the entropy of the metal, are you assuming that it's reversible?
No, the calculation goes through reversible path. But the process, I can just drop this metal into water, right? I can just drop it in there, right? The whole thing is irreversible, right? But I can still calculate the entropy change. That's what I'm saying. So the process is irreversible, right? Dropping this metal, hot metal into cold water is irreversible, right? But to find the entropy change, you have to find a reversible path that connects the initial state and the final state, right? That's how you calculate it. Right? Once you calculate that, then you know that's the entropy change, right? Doesn't matter whether the process is reversible or irreversible, right? At least for the entropy of the system, right? The entropy of the universe is something else.
I have a question.
Yes.
Wait, so that equation that you wrote down earlier, where you said that SB minus SA is greater than the integral of dq over t,
Yes.
it's irreversible. Would that mean in this situation, because it is an irreversible process, that delta S isn't actually what we calculated?
No, delta S is what we calculated, right? For the entropy change, right? But but for the irreversible process, for this integral itself, right? This is what we calculate. We don't know what this number is. All we know is just less. Right? That's all we know. A lot of the time, thermodynamics only put limit on what's possible. Right? Say if you're designing an engine or if you're looking at the chemical process, right? You calculate Gibbs free energy, you calculate Hemsworth free energy. That only tells you that puts a limit on say that in particular, right? Hemsworth free energy, right? You calculate the number. That tells you what's the maximum amount of work you can extract from the chemical reaction at the constant volume. Right? So that's a limit, right? You can never calculate it because when something is irreversible, it's almost like friction, right? When you have friction, sometimes you cannot really calculate what's happening. Okay? But you can put limit, right? And that's what this does.
Okay.
Question? Any question? If no question, then I'm going to stop and then move on. Okay, that's the end of our discussion on thermodynamics. If you're interested in more of the subject, like physics 112 or I don't know, chemistry classes. But for now, we're going to go back or should stop it into electricity and magnetism. When I say go back, I mean that we should go back to study something that's more fundamental in the sense of interaction. And from, let's say, we already know a little bit from physics 7a that let's see. Let's talk about gravity a little bit, right? In just a moment. Right? For gravity, what do you have? The force between two particles and one and two. Okay? Now separate these off, right? The force is given the force of gravity. By the way, 7a is a required part of, it goes over, right? In the midterm, I don't have to assume anything. I can just, have material coming from 7a, right? But it's a G, M1, M2 over R squared, right? And of course, force is a vector, right? Okay. And what is the direction of the vector? The direction is where there's negative sign because gravity is always attractive. Force. Because of Newton's third law, equal and opposite sign, right, in the direction of r. Okay. Okay. And let's see, if there's this two thing in the universe, right, the only direction defined is along the axis between n1 and n2. So if there's this, if the universe is homogeneous and isotropic, you cannot define other direction. Right? There is only that direction. Okay? And then from the study of general dynamics, I don't know, you guys just slapped that? No, you guys have, you guys take 7a, in H7B, there's an equivalent book of this, right? It's an MIT series called Gravitational. It's actually a good book on mechanics. Or in general, in general too, we know that the change in kinetic energy, right? If I have a particle or something, right? If I have a particle and I do work on it, right? Then the change in kinetic energy is that E 1/2 mv squared final minus 1/2 mv squared initial, right? That's equal to the work done on system, right? In the bottom. Okay? So in this particular case, then it becomes, because the work done on the system, you have to apply a force opposite in this particular case, gravity, opposite the force of gravity itself, then you have a minus sign. So from initial to final, force of gravity, say, right, and okay. And we find that this is just to summarize the result from last year. This is then equal to, if we calculate this, then this is equal to the energy at the final point minus the energy at the initial point. Right? Do you recall this from 7A? I'm just trying to summarize, right? So then we have a conservation of mechanical energy, right? Rearranging that, I have 1/2 mpi squared plus ui, right? It's equal to 1/2 mp final squared plus 1. Okay? This is a consequence of Newton's law. Okay? And for gravity,
That's the sure out, or if you do light and minus on both sides, then what happens is
did I make a mistake somewhere? I might, right? I'm going to set up my sign. Oh, this is plus, sorry. What is that minus sign somewhere? Did I make a mistake?
I think it's fine. But if you subtract, it has minus on both sides, that's fine. File with that again.
Right. So if I put this to the other side, there's a minus sign here. Right? Did I make a mistake?
Yeah, it's time to move
It's just
on.
saying you need to flip the final and the initial for the potential.
Oh,
Yeah. This is negative value, subtract.
but this is a conservation of mechanical energy says that the sum of kinetic energy plus potential energy is.
Never mind about that.
Is there a minus sign here?
Yeah,
Why is there a minus sign here?
Because if potential energy increases, kinetic energy must decrease.
Right. Okay. Yeah, I might have made some minus sign somewhere, right?
You have it in front of the interval. It's just when you evaluated the interval, you didn't keep minus.
Yeah, something like that.
No, it's there.
Anyway,
You're good.
is it okay for now? I may have missed a minus sign somewhere. I'm confused now. I don't have it in my notes. But the final result is correct. Okay, I'm very good at my minus signs. You know, I don't know why. Are you guys okay with minus signs? I usually, in the end, I justify it with words because with the math, I always lost a minus sign. For gravity, we know that the energy is given by, if I just do particle, right? I'm just going to go through this fast because I'm just motivating a discussion on electrostatics. Gm 1 and 2 over R. Okay? So if I draw it, right? Mu, which is R, the potential is like that. Okay, it's 1 over R potential. Okay? And another thing is that gravity also satisfies principle of superposition. Let's just do it. Gravity also satisfies principle of superposition, right? Okay, let's just stop here. Okay, let's just stop here and discuss this in the context of electricity. Any questions so far on this? Okay. So it turns out there is another interaction. This is one of the fundamental interaction in gravity, right? It turns out there is another one that is called electricity. Since every atom is actually charged, right, then it affects almost everything that you see, much more than gravity, right? Electricity satisfies very similar equation. except for two things, or a few things, right? One is that it's much stronger. How much stronger?
1 to 37 times?
37 times? I don't know, suppose you have a proton. Is it in the book? Maybe in the book. If I have a proton and an electron, right?
Oh, that's like 30 volts or something like
34. It has a gravitational interaction because of the mass, right? Because a proton has a mass of, I don't remember, you guys remember? 10 to the minus 27 kilograms. And the electron has a mass of 10 to the minus 31 kilograms. Something like that. It has a gravitational force, right? But because a proton is charged, a proton has a charge of plus 1 E, and then an electron has a charge of minus 1 E. Right? It also has an electrostatic interaction, right? In this case, it's effective electrostatic. Right? And this force is actually 10 to the 4
Mm.
10 to the 4
37?
You're close.
So as far as an atom is concerned, right, you care less about gravity. In fact, for most things that you study, unless it's astronomical in size, you could care less about gravity. Okay? All you have to worry is electricity and magnetism. And the reason that you don't see this, right? The reason that you don't see this on a macroscopic scale is because there are two kinds of charges. Right? It's called positive and negative. I think it's Benjamin Franklin who first coined his name, positive charge and negative charge. And like charges repel, unlike charges attract, right? So if you're positive they repel, okay? Negative and negative, they also repel. But if you're positive and negative, then they attract. Okay? And the reason that you don't see these kind of forces is you have a perfect balance here, right? Plus and minus. Okay. So if you sum over all the atoms in a crystal or in liquids or in whatever, right? Then because there's a perfect balance between plus and minuses, then all the electrostatic forces almost cancel out. Okay? And that's why you don't see it. Okay? That's why you don't get suddenly you get propelled all the way to the moon. Okay? So the force between two charged particles is given by Coulomb's law. Let's use the first one formulated, right? If I have two charged particles, Q1, point charge here in this case, okay? Just all this is stabilization, or I'm trying to swap a lot of things under the rock. Q2, right? And the force between them, Coulomb force, it's proportional to the charges, right? Q1, Q2. So it's very similar to gravity, right? Gravity is G(n)(1) and Q over R squared. Q1, Q2, okay, over R squared times K in the direction of R, right? So when Q1 and Q2 is positive, then they actually repel. That's why there is no minus sign. In this case, there is a minus sign. Right? Is that if they are unlike charges, then you get a minus sign. then the force is attractive. So it is plus and minus, plus, minus. Okay? And K is given by some completely arbitrary definition of the charge. So give you a huge number, minus 9 10 to the 9 Newton meter square per Coulomb square. Right? The unit of charge is called Coulomb. Okay? And sometimes K is written as 1/4π∁0. Okay? This is a more common description here. You'll see epsilon naught everywhere in electrostatic and in electricity and magnetism. And epsilon naught, if you calculate it, it becomes 8 point. Does anybody remember 8.85 times 10 to the
-8.
-12?
12.
You just throwing out numbers?
What was it?
I'm off today.
Simply -12. Right? With the property limit, because the inverse of that c squared over Newton meter squared. Okay?
I had a question about the force. So if they are attracting to each other, then the force is negative?
If yes,
Or-
if attractive, then the force is negative.
Okay.
Right. So that's why it's down, right? Attractive. Then the force is negative. Right. Repulsive. And just as usual, if you're like me, then I usually draw it, right, and then decide whether it's plus or minus. And when you have unlike charges, then it's attractive. When you have like charges, then they're repulsive. Okay. Also here in this case, if there's only two things in the universe, right? If there's only these two charges, the only direction that's possible is radial. Right? So in this sense, it's similar to gravity. It's a central force, right? Okay. Force is radial. Direction. Restore the central force. Okay. So when you have a central field force, you know that you can define a potential, and we do the same thing here. Let's see. Before we do that, no, let's do that first. So just similar to the discussion of the gravitational energy, right? It is also electrical energy. So let's do that more slowly here. That's the force. Oh, do you think I'm wondering, let's do things slowly because we have a lot of time now. Let's calculate the work done, right, in bringing two charges. Work done in bringing Q1 and Q2 at the distance r apart, not infinity. Right? Two charges at infinity, right? Positive charges there, right? Bring them close. Right? I have to do work because they repel, right? They repel, I have to push them together. so that they become next to one another at a distance r, right? How do we calculate that? Okay, so the work done then is equal to integral, right, from infinity to position r, right, f Coulomb, right, with a minus sign, right? Okay, and the reason we have a minus sign is because I have to do work, right? Okay. Times g naught. Okay, and this becomes a minus from infinity to r k q1 q2 over r squared q1, right? So r1. Okay.
Why are the charges lowercase? Does that mean anything, or? Okay.
Minus.
Wait, aren't they always?
Oh, is that right? It should be lowercase, right? Okay.
Wait, what does big Q mean?
The
Oh.
big Q is what it
Yeah,
doesn't
okay.
look right. When I write it, it doesn't look right.
Q1 little one, big Q.
Yeah, it's like
Looks
that.
familiar, right? Yeah. So suppose, to calculate this, suppose Q1 is over here, right? And I have to bring Q2 all the way from infinity over here, where I have to bring it in some position R here, right? And we want to calculate this work, right? Okay. So how do we do that? It's of course path depend. In this case, the integral depends on the path, right? Is this clear so far? I see a lot of confused faces. I just want to derive the whole thing rather than just give you the result just like gravity. I think at the end result is very similar to gravity. Okay. So let's look at this integral here, right? Integral minus from infinity to r, right? So because of the minus sign, I can flip this, right? It's become an integral from r to infinity. I remove the minus sign. I have k q1 q2 over r squared in the direction of r, right? Times dr prime, right?
Why is it prime?
This is just a different value here. It's like we call it ds, right? Is it better with ds? We'll call it ds. This is along the path. So if I just look at a particular point here in space, right? This part of the integral, I'm integrating from r all the way to infinity, right? And I look at the particular ds, right? Okay. The force here, the force at this point, right? Because Q1 is over here and Q2 is over here. Then the force is in that direction. Right? This is the direction R. Okay, and this is the direction of the line integral, S.